Okay, well, we're at 1 minute after the hour and the recording started, so let's get started. Welcome to the Air Sea Fluxes from Space webinar series. Today we have Meghan Cronin, who's going to talk about in situ validation for satellite opportunities from space. And this is particularly timely because as we talk about concepts like Simmerflux or Simmer-C, which Shannon Brown discussed back in February, the big question that arises is how will CalVal be done? What are the in situ opportunities? And so it seemed like it was exactly the right moment to talk about this. And I'll let Meghan take it away.
All right. Let me start sharing my screen there. Can you see it?
Yes.
Yes. Okay. All right. Well, thank you, Sarah, for this invitation to give this talk. We were there in Ocean Science meeting last week when we were talking about all the future of all of these satellites and opportunities. And of course, um, well, before I get started too, I put this together just in the past couple of days. So I do want to thank other people who helped me with some of the slides, including Ruth Patterson. I took a lot of slides from her town hall meeting presentation, and Katie Coleman, Adrian Sutton contributed some figures, Ken Connell, Billy Kessler, Dongxiao Zhang from PMEL and SECOS UW helped review my slides. Okay, so the Global Ocean Observing System should be considered as a backbone for observations for CalVal, satellite CalVal. That's really my big message here. And the Global Ocean Observing System, GOOSE, comprises networks, various different networks, some more directly relevant to satellites and some maybe less so, but all of them are useful. I will be talking about the Ocean Sites Network and Sunfleet. And really, ocean sites should be the go-to observations for in situ satellite invalidation. These are arrays of surface moorings and subsurface moorings. This map is showing all the surface moorings with the big squares have full flux, so air, you can compute the bulk air sea heat fluxes, momentum fluxes, moisture fluxes, and they include radiation, solar and long wave radiation, as well as, the meteorological measurements that include wind speed, direction, sea surface temperature, air temperature, relative humidity. So these big squares have a lot more measurements. There's some really great ones here, like the Erminger Sea, Stratus. I'm going to just show you a little bit about Papa and Kio. These are two sites that I maintain. This is part of the Ocean Climate Station project that I lead. Here's the website for the data downloads, and you can just click on what variables, what time period, and if you want ASCII or NetCDF, and deliver the data or display. Here I'm displaying the data. You can see Papa has had a surface mooring out there since 2007. So these time series are really great for comparing to satellite measurements and as well as to model measurements. Here is Kio. And what you can see, COVID really did a number on a lot of the ocean sites moorings, including Kio. And so we had a very big break because we were not able to maintain, send out a ship. And since then, Keo, we have had problems getting a ship to this location. And I have to say, this is common for a lot of the moorings. And so this is a time where if you really like one of these sites, you should be helping to advocate for these sites. This is all of these ocean sites time series are endangered and need advocacy. Now, I made this figure here in June 2023 for a paper that I did describing the Ocean Climate Station project. This block here is Tropical Pacific Observing System. And in fact, that it is now been redesigned and is in the middle of being upgraded. Now, back in 2014, there was again, ship time problems led to a big downgrade or, well, loss of data of these moorings. And so the international community got together and started thinking about how to make the array more robust and sustainable and more capable. And that was the TPOS 2020 project. And there's a set of reports here. And they made recommendations to have fewer moorings, but more capable moorings. And so rather than having just the MET, these meteorological standard moorings that measure wind, air temperature, relative humidity, sea surface temperature, and the thermocline, we also want to just add a few extra sensors and get the full fluxes. So you have rain and solar and long wave and barometric pressure, and also resolve the mixed layer depth. So that's the tier 1. A tier 2 also has a shallow current meter. Okay, so that's tier 1, tier 2. And then there's tier 3 moorings where before there was a nearby ADCP, that's an acoustic Doppler current profiler that was about 5 kilometers away, providing current profiles. But that's a subsurface mooring, and so we would never be able to have that data in real time. It was always you recover it, and then years later you see the data. So now the ADCPs are going to be mounted on the line and in a kind of a series so that you'll have the full current profiles from 250 meters up to 8 meters or so, and then a shallow current meter. So that's a tier 3 mooring. And and so this is the array design. You see there's going to be fewer moorings here. Those are discontinued sites. And then these blue diamonds are the tier 3. We have some new sites at 1 north and 1 south, 140 west. So we really are going to be able to resolve the equatorial undercurrent transport here at 140 west. And then tier 2 are along the equator and in the equatorial band. And then a few up in the ITCZ. There's also some new sites that go into the ITCZ, and what else? Yeah, fun stuff. Okay, the other thing that TPOS 2020 recommended was to do some process studies, and 2 process studies are going forward. One is called the Tropical Pacific Observing System, TPOS Equatorial Pacific Experiment, that's TPEX, in the eastern Pacific domain. This is at 140 west. And this is to resolve mixing where you have upwelling, but also there has to be some kind of a mixing really that is associated with the equatorial cold tongue here. And there's really sharp fronts, and so lots of air-sea interaction. And this field campaign had been planned for this past year, or 2026, but is postponed till August, November 2027 due to a fire on the Ron Brown. But this is going forward. And yeah, and that's I think all the PIs are identified, they have their money, and they're planning away. And then there's also this field campaign for TPEC-C to look at the processes governing the migration of the eastern edge of the warm pool. And this campaign is delayed. It will happen after TPEC-E, and so it's likely to be spring of 2028. But some parts have gone forward, so I'll show you here. I actually had a project that got funded or is planned to be funded and partially funded. It has been partially funded already to put out some spare equipment from PMEL and AOML and NDBC onto the moorings. And so we are now going to have a lot more salinity, a lot more acoustic profiles off the equator as well as on the equator. So we'll be able to look at not just zonal processes, but also meridional processes associated with the equatorial, the eastern edge of the warm pool. This is in the water already. So this is, and assuming that money flows as it's expected to, then we would have a postdoc opportunity here at NOAA PMEL. So watch out for an ad for that in summer or early fall this year. And this project is in collaboration with Ranellis and Greg Foltz, Ranellis Perez, Greg Foltz, and NDBC. Okay. So that's all the fun stuff. And now for some of the harder news. There's this paper by Riccadulli et al. That showed that comparisons between the satellite winds and let's see. Okay, deep. This is showing that the comparison of the satellite winds and the buoy, the Tau buoy winds, suddenly had a very big increase in their differences starting around 2020. So that the Tau winds are reporting about 10% higher than all of the satellite winds, and it's about 0.5 to 0.8. And what's happening? They traced it to the change in the NDBC wind tunnel that happened in 2019. So we have been actively working on this within NOAA, and just a couple of weeks ago, 2 weeks ago, NDBC sent a whole group of people to PMEL, and and we have been working to confirm this, identify exactly what's going on, and then figure out a plan for remedying this wind bias. So they have sent a set of sensors, PMEL sensors, and NDBC sensors to 3 different wind tunnels, and have confirmed that indeed the NDBC wind tunnel is at present not NIST traceable. And so that means that the tau wind measurements made since 2020 should be used with caution. So right now, NOAA NDBC is working with the National Institute of Standards and Technology, NIST, and with PMEL on the next steps. And we don't quite have the exact plan until, we're done in this phase of evaluation and, working with NIST on the guidance. But what we can say is that NDBC will deploy only manufactured calibrated RM Young wind sensors until the new calibration procedure is adopted. And the biased calibrations will be removed from that historic data, the 2020 to 2026 tau WIDS. Exactly how, whether it will just be going back to the manufacturer calibrations or doing some other kind of calibration, we'll have to see, and we'll be working with NIST on that. In another thing that we will do is do a stability analysis on the calibrations. So if we are, looking at the calibrations, PMEL does calibrations using our wind tunnel after every deployment, pre and post, and we can look to see how those calibrations change through the lifetime, 10 years of a wind sensor, and see whether those calibrations remain stable, in which case, going back to the factory calibrations might not introduce much of an error. From our preliminary analysis, it appears that going back to the NDBC, or going back to the factory cals and just using those will improve this calibration problem that was identified by Riccadulli et al. Then the other thing that we will be doing is a shore-based intercomparison of the NDBC, PMEL, and possibly Woods Hole buoy systems. And that's planned for a start in this coming fall, and that will test the entire system. So lots of work there on actually really understanding what the calibration process is and the best practices, and making these high quality measurements. Okay, now for Sunfleet. And Sunfleet is the surface uncrewed fleet, and there are many different types of uncrewed, surface uncrewed vehicles, as shown here. And so you're probably wondering, well, how good are they, right? How well do they compare? So this is a study done by Dongxiao Zhang in 2019, where we had the sail drone buoy just do squares around the spurs, the Woods Hole buoy that was deployed at 10 North, 125 West as part of SPURS. And here are the intercomparisons. These are just figures from the paper. And I pulled out some of the stats from the tables there. There's the sailed run is just slightly higher by 0.3, let's see, 0.3 meters per second. But overall, we were all very pleased with this intercomparison and felt that while there is some scatter and some slight differences, overall, this was agreement to within expectation of the expected uncertainty. This is another interoperability experiment done by Greer et al., Luke Lennon, and Tom Farrar, and using the wave glider. So now, and using the flip as the reference here. And this was really super exciting because, this wind sensor and air temperature are right on the water. And so there had been a lot of concern that the winds measured at 1 meter or, whatever it is, actually, it's very close to the surface, can't be considered as winds for the overlying air. But in fact, when you use the bulk algorithm to adjust the variables to a standard height, and in this case, I think they were adjusted to the height of the sensors on flip, then the agreement was really very, very good. And they did have to cut out sometimes when the, water, when there was, I guess, these overturn or get into the water. But it didn't take long for them to dry out. So as long as you keep track of when that happens and you cut out that time, then these very small drones appear to be excellent platforms for using for all types of analyses, and they compare well. And so what this means really for the satellite is that the uncrewed surface vehicles, whether they are small or large, if they've gone through these kind of tests, we can use them as to provide matchups and triple point opportunities for satellite CalVals. Okay, and for other types of studies. So we are, through OASIS effort, we have made this into an emerging network of the Global Ocean Observing System. And one of the major requirements for doing that was writing this paper here that was led by Ruth Patterson, that looked at all the different attributes of a goose network and how that was related, how the uncrewed surface vehicles met all of those different attributes. This paper here had 52 co-authors from 9 countries, had 9 ECOPs, 5 PhDs, and 200 data sets. Here are the data sets that were reviewed in it. And you can see that the Sun fleet has different regional foci in the tropical Pacific observing system, in the Southern Ocean, in the Bering Sea, in the Atlantic hurricane regions, in coastal surveys, and then there's also a whole patchwork of process studies. And together, this makes a global network. So I am, and you can see that they are being used for a whole wide range of different kinds of observing different phenomena, from ice edge to marine heat waves and some mesoscale fronts and all sorts of things. So I will now talk to you about our lessons learned and our plans for integrating uncrewed surface vehicles within the tropical Pacific observing system. And we have been working on this for about 7 years. Here's the kind of a spaghetti diagram of all of our different missions. And, some have had 2, some have had 4. So this is now what we've learned from that. This is our observing strategy. You have to, with these uncrewed surface vehicles that depend upon wind for propulsion and you have and are in low wind, high current regimes, you really have to ride the currents. And so the plan is to go westward along the equator when you have, to catch the south equatorial current. And then you go northward along the mooring lines to get these repeat transects and to do the interoperability experiments. And then eastward along the north equatorial countercurrent, which is dynamically linked to the intertropical convergence zone. And so that's where you can get your convective activity, be observing that. And at the corners of these transects, you can do process studies. And then, of course, as El Nino are developing, you can do adaptive sampling of El Ninos. I call this pattern here Go USV. It's kind of a take on the Go Ship idea. Go Ship is full water column, once per decade, try to get but what we're doing is air-sea interaction. So really what we want to resolve is the annual cycle. And whether that's with the, combined with the Tau tender research vessels and the USV, our goal would be to try to get resolve that annual cycle. Okay. And then I can say here that we have actually a mission coming up in this summer, in August. It will be leaving Hawaii around mid-August, and we'll have 2 drones go to 140 West, and then 2 drones go to the eastern edge of the Warren Pool. And this will be both in 2026 and in 2027. And so we will be able to coordinate with the TPEX-E people. All right, so this is not just a process study. It's these data are serving many different applications and interests. We have data that is going on to the GTS. And so with the barometric pressure, air temperature, humidity, wind speed. And so this is serving marine weather and subseasonal to seasonal forecasts. We also try to have at least 1 drone with an ASV CO2 system. And so that is really good at providing measurements outside of the ship tracks and the traffic lanes, ship traffic lanes. So this helps fill out the the SOCONET maps for CO2 uptake. And the outgassing on the equator in the Eastern Pacific is really important to resolve, as it is one of the largest uncertainties in the global mean CO2 uptake assessments. Okay, now we've been always sending out at least 2 drones at a time. And at first that was just because we wanted to make sure that we were successful. But we've realized that this can be used as a mesonet. So this was a couple of papers by Samantha Wills really showed this. Here we have, you can see convective activity or rainfall patterns in the shade here, and we have the ECMWF reanalysis winds in blue on their grid points. And here is the 3 or 4 drones, and it was actually near Town Buoy. And now zooming in, you can see how all of the variability that is missed in this, the ERA5 reanalysis. The winds in the ERA5, that's the blue, are all kind of uniform, but in fact, what we're observing are these big gusts, these big strong winds associated with downdraft cold pools that happen in the convective area. So it's like when you're standing on a ship and suddenly the wind picks up, you get this cold, dry air on your face. As this cold, dry air downdraft comes down and pulls out. And so we can observe that. And we see it pretty often when we go into the ITCZ area. And Samantha made some composites, and these can be used as model tests and as satellite tests also. The roving mesonet concept also works for the ocean. And so Katie Coleman, who's a graduate student at UW, has been looking at using these to see abrupt fronts. We're finding that abrupt fronts are ubiquitous on the northern edge of the equatorial cold tongue. Here's an example. And this is just, it's not a smooth going from cold on the equator to warm. It comes in these big steps that can just be, less than a kilometer. How do you observe that? The uncrewed surface vehicles and the roving pairs or swarms of the drones are excellent at capturing that submesoscale variability. And also for observing upwelling through observing the divergence or convergence of flow within that swarm. We can do coordinated work with process studies. There was the motive process study that took place last year, and we actually were able to coordinate with that. We had a wire walker sandwich on Thanksgiving Day, where 2 sail drones were on either flanked the wire walker as it was drifting in a tropical instability wave crest here. And then, of course, we can do adaptive sampling for developing El Niños as we did in 2023. And you can see here how, the actual definition of the eastern edge of the warm pool can be very mushy. And these meridional processes look like they are going to be really important to understand. Okay, and so that's my little take on how our vision for Sunfleet within the tropical Pacific observing system here. And so last week, gosh, it feels like a long time ago, we had a town hall at Ocean Science meeting. It was the Sunfleet, a newly endorsed emerging network for the global ocean observing system. And Seb Swart, who I think is on this call right now, was part of this. Eugene Berger, who is actually funded to develop a data portal for this, and Ruth Patterson, who, of course, I stole a lot of her slides, and Marcel Duplessis, who created this QR code for a survey to join Sunfleet. So if you could take out your phones, if you're interested in, if you use Sunfleet, if you use uncrewed surface vehicles and would like to be part of Sunfleet, or if you're a student who uses the data, or a postdoc, or somehow involved, then pull out your phone and sign up to join the Sunfleet. And we're kind of forming what this is. It'll be a little like, it'll have some things similar with other parts of the global ocean observing system, like have governance structure with a steering committee and a science committee. But it will be in a data committee, but it will also have some unique parts that are, because it's a new and, has a lot of public-private partnerships, and we we're figuring this out as we're going. So we need your help. And if you're interested, then please join by signing up here. Okay, so in summary, the Global Ocean Observing System provides a backbone of in situ observations for calibrating, validating satellites, and the Ocean Sites time series should be your go-to data set for assessing weather models and the satellites. Tropical Pacific Observing System is being redesigned to have fewer but more capable moorings, and there's TPEX process studies that will be taking place in the next 2 years, right? And we have enhancements happening already. The Sunfleet, that's the surface uncrewed fleet, was recently endorsed as an emerging GOOSE network, and it provides opportunities for matchups and triple point calvals and process understanding for unresolved variability. So the other really big take-home message here is that interoperability experiments are really, really important, and they should be done at every opportunity. There's so much that can be learned. And okay, and so we really thank the satellite community for doing this on a regular basis, and finding the bias problems with the tau winds. And NOAA is working to remedy this. And in the meantime, the winds from 2020 to 2026 from the tau winds in the tropical Pacific should be used with caution. But we will be reprocessing those winds and remedying the calibration procedures, updating the calibration procedures. Okay, any questions?
Well, thank you, Megan. This is fantastic.
Uh-huh.
And yeah, questions. Maybe while people are thinking, I'll ask about the challenge of getting uh, CalVal or interoperability for high latitude regions.
Um, well, okay, that's going back to the ocean sites and okay, this map here for the Sun
Mhm.
Fleet, there is actually um, a lot of Sun Fleet interest in the Southern Ocean and in the
Mhm.
higher latitude, so there is opportunity there. Um, and and then if you consider the ocean sites, there's a few, not as many, um, but there is a few. Um, Here's the SOTS
Mhm.
site. It was really sad to lose the OOI site that was off of Chile, um, but there is some there.
Mhm. Yeah.
And there's,
So I
um,
guess the question is, how much do we need to have
yeah,
confidence? And that's
I see that
the
Seb
question.
Swart is on the
Yeah,
line.
Seb had his
And
hand up, so I'll agree.
okay.
Yeah, I mean, it was exactly my question too was how do you, pretty much what Sarah's asked, but of course you're showing all these interoperable experiments or CalVal with other instruments in the water or even satellite products. And many of these are really based around the tropics, like you have 10 degrees north and Luke Linane and their work is also in not pretty terrible conditions. So I was thinking, how is this done for much rougher places like that are have really high swell conditions and our uncertainties related to how the wind shadowing impacts measurements near the sea surface from USVs and how we might get there if you had some opinions about it
Um,
how it would be the best way to approach this.
yeah, well, there has been a really big effort to have USVs within the hurricanes. And um, and I think there might be a few people on the line from those projects, and perhaps they can talk about it. But I know, um, I don't know if I'm jumping ahead here, but um, I know that Dong Zhao was telling me just yesterday that the hurricane people are really interested in looking at the actual um, aerodynamics of the different platforms within those really super high wind conditions. And maybe some of those people can speak up here.
Yeah, Megan,
The
you
hands.
answered well. Yeah, we have normally every year we have 10 to, now almost 20 USVs that dedicated for the hurricane observation. Of course, during those extreme conditions, we don't have this luxury to intercompare different platforms with fixed known high quality measurements such as buoys that we have been deal with for decades. We don't have those co-located observation for sure. So it's very hard to learn the quality of the measurements. So one idea was to use more of those, wave tanks, wind tunnels, putting models to learn those aerodynamics around those structures. The main concern was the flow distortion, of course. Yeah, we are learning. But we did compare, I mean, the satellite community actually compared the satellite observation, specifically the SAR for high resolution, high extreme wind regime with the sail drone observation. There's some great agreement between those cases, although very limited. Yeah, we are learning.
I see Lev has a hand up. Lev Looney.
Yeah. I guess I missed, I think, the beginning of your question, Seb, but if my understanding was proper, it's asking about how these USVs do in more extreme conditions, especially the larger waves, and how you can compare with other platforms. Is that correct?
Yes, I would say so.
Yeah, I mean, I think one of the biggest challenges is you get to this fundamental question of what is it you're trying to measure and defining that. With TCs, right? If you're talking the standard 10 meters above the surface, but you're in waves of 15 meters, that's a new challenge that I don't think there is a proper answer to, at least one that I've really heard that is accepted throughout. And I've asked more of the hurricane operational centers, but I think overall, yeah, the vehicles do fairly well. But like Dong Zhao said, it's really difficult, and we're measuring in ways that have never really been measured before. The moorings typically they don't go through hurricanes, and the ones that do not get the high res data as much. So what does, for example, 20 hertz winds even look like 3.5 meters above the surface? How do you know what is good and what's bad? There's definitely some of that flow distortion, but just because something looks not natural, is it truly not natural, or is it something we just haven't really observed before because we haven't had the capability to?
Thanks. Luke, you
All
want to go
right,
ahead?
I'll jump in. Thanks, Megan. This was a very nice summary of some of the activities that you guys and other folks have been doing. To go back to Seb comment, I think it's not just hurricanes that he was talking about, it's also swell, which especially if you go to Southern Ocean, you don't necessarily have very high wind. I mean, we have a vehicle right now, wave gliders, north of the Ross Sea, that was getting 8 to 9 meter significant wave height in 10 knot winds last week. And then you get into issues of interpreting the data because you really become, well, this assumption of a wave following frame versus, doing fluxes relative to a mean sea level becomes a big deal. So to answer Seb's question, I think it's a research topic. And I think though there is no intercalibration because we don't have a flip, in the Southern Ocean, there is still a lot of things that you can do, especially with multiple vehicle, and helped by some numerical simulation.
Thanks. Other questions or comments? Luke still has a hand up, but I'm thinking that's a leftover, so we'll go to David Wolf.
Yeah, I mean, I think if you go back to the original objective, of course, it's about having algorithms for satellites that are robust to a whole diversity of sites. So it's basically, I mean, it's the same question, but put slightly differently, thinking about that as an objective. And I think I agree with Luke that, I'd be more worried about, can we do the algorithms that get tested and perfected for the tropical ocean actually work in the Southern Ocean or the Northeast Atlantic in winter? And I think there's probably a sort of theoretical approach to this, thinking about what diversity of, if you like, prime high-grade sites you need in order to prove that a satellite algorithm is generally globally robust. Otherwise, you end up with lots of regional biases.
I like that answer. It seems to get to the root of the question I was asking. So I see Jim Edson has a hand up.
Yeah, I just want to, it's not shown on this map, but the flux buoy at the tip of Greenland there in the Erminger Sea is an excellent platform for doing some of these comparisons. And all I can say is that I'd love someone to check this out as well. But you can say something about the quality of the winds when you compare, say, direct covariance fluxes against, say, bulk parameterizations. And there is some, if you do get good agreement between those two, that does say something about how well your winds are being measured. So that site that you see now, I am so happy to share that data with anyone who wants to look at that, and also to compare that site with what you're seeing in the Southern Ocean. We have over a year of an amazing data set that people are still using. We're talking right now about perhaps getting that site back, but it really does show the difference between sort of a fetch limited sea, which you see in Erminger, and a fetch unlimited sea that you would see down in the Southern Ocean. You get much larger waves, but they're swell like, and so they don't have the same roughness as you would see in the Erminger Sea. So, and you don't need a hurricane to look at these things. You're routinely getting winds above 20 meters per second, which can tell you a lot about the quality of your measurements and what you're seeing. So I just wanted to point those two out. Those are two OOI moorings. Like I said, we're trying to get something back off the tip of South America, but we do have data sets, and like I said, I am making these as available as I possibly can. But please just email me, and I'll send you these data sets for you to work with. And that's it.
Is there a direct covariance flux system on the SOTS buoy south of Australia, south of Tasmania?
Not that I know of. We've been working on just that for, I guess that was a couple of years ago, and then we were sort of overcome by events, I have to say, and we were not able to follow through. But I would very much like to see a direct covariance package on that mooring. They've done a heroic job, I think, of keeping that out there and making those measurements. And that, along with trying to get something off the tip of South America, would be just amazing if the community could sort of get behind that.
Can I just say that all the operators of these moorings are heroes? It is so hard to get ship time for all of these moorings and to make this all work. So they all need advocacy and love, and if you use the data, please reach out to the operators and work with them and help them.
Yeah, and just Meg, as you know, we're trying to add these as best we can, add these flux packages, and the most recent one is Papa.
Right.
And we're putting together another unit for deployment on Papa for this late spring, I think, early summer.
Yep.
To have and that is also a really great compare and contrast with Erminger Sea. You have much more fetch there, much more than you do in Erminger Sea, so you might expect different wave conditions and different fluxes at the same wind speeds. So, there's a lot that can be done with the measurements that are currently existing. So, contact me and Meg and anyone and the rest of the team, especially those that, like I said, are working down off of Australia on that mooring. That's been an amazing job. I'm done.
Can I ask, following up on that, can I ask about the prospects for flux covariance systems on Sunfleet?
Yeah. Well, I can say we the wind sensor that is on, I think, almost all of these uncrewed surface vehicles is a three-dimensional wind sensor, and so we do measure UVW at 20 hertz, and I think I saw Jack Reeves-Iyer online here, and he has written a paper about computing direct covariance fluxes. I don't know if he's still on here.
Yeah, I mean, I could speak to that.
Yeah,
Jack did a great job with that paper. He convinced me that you can make these measurements from a sail drone. And especially since you already have the three-axis sonic, the addition, do you have say a microstrain or something measuring the motion of the drone? Because that's
all of
a,
them have IMUs, very good IMUs. Yes.
you do. And so all you need to measure is the vector R from that IMU to the sonic, and you can measure direct covariance. And that's basically what we did with Jack.
And
Right.
now I'll jump into like not all USVs are created equal too. I mean, sail drones are nice because those observations are pretty high up.
Yeah.
When you get much closer to the surface, you have to be careful. Even if you have the instruments, then you can't. You have to start factoring in the static pressure, slope term as as you get closer to the surface, and um, that's much harder for bulk fluxes, like those low-lying kind of USV works well. It's more complicated for eddy correlation fluxes. But if you go high, I mean, we've been trying to put very large mass on wave gliders. Or what Jim is doing with those drifting spar buoys, which are amazing too. So.
But Luke, because your inner comparison with Flip was so good, that indicates that your flux algorithm and the log layer dynamics must be working pretty well, right?
Well, I mean, the bulk flux, yes, not the eddy covariance one. We didn't do eddy covariance intentionally. But then there are caveats, and we go through this in the paper that explain, for example, um, why Togacor 3.5 is works better than previous version when it comes to wave contribution, and we shouldn't use. I mean, it looks like those J-wave parameters, for example, shouldn't be used. It's just it's based on the data that are being assimilated into those parametrization.
Good to hear.
Yeah, I mean it's really cool actually. I mean, I'm sure you read the paper, Jim, but
Right.
it's
No, it's
like
really good to hear.
it's funny that like in 3.5 when we added a bunch of your buoy data, then all of a sudden, the standard parameterization kind of like indirectly incorporated all those wave effects better than previous one, which is pretty neat.
Yeah, I think one message there, Luke, and this is great to hear, is that to a large extent, it's not the algorithm. That's the problem. It's the measurements.
Yeah. Yeah.
Right. And so when you get a bad flux, don't blame the algorithm necessarily. Blame the measurements.
Yeah.
And because it's a hard, like you're saying, these are hard places to measure.
Yeah.
Well, we are at the end of an hour. This has been a great discussion. Thank you, Megan, and thank you everyone for
Thank you,
participating.
Megan.
Yeah.
It was great.
Thanks so much.